Okay, let's get started. It's my pleasure to introduce Maria Navarro Gastiasoro, who's going to be the community seminar today. Maria did her PhD in the University of Copenhagen with Brian Anderson, and then she was a postdoc in the University of Minnesota with Chulkov and Fernandez. And then she was a Marie Curie Fellow at La Sapienza in Rome. And since 2023, she's Ramon y Cajal Fellow here at the DIPC. And since she's going to talk about all that she did, I let the curtain.
Thank you. So good morning, everyone. I think, actually, I've been here for 2 years now, and I think I can say I know most of the people I see in the audience. I guess it's good because probably many of you also more or less know me. But today I wanted to give you like a taste or a glimpse into what the type of projects that I work on. And it's supposed to be like, I try to do it as broad as possible. I think I have maybe one equation or so. It's more about the motivations of different things that I'm working on and the type of methods we use and so on, without getting into detail. So this is supposed to be, I guess, rather informal. I know that there is some chemists in the audience, maybe from other, I don't know whether there is any astro, cosmo people, but like at any point, yes, raise your hand, stop me. So let me get started with the acknowledgements. Most of the stuff that I'll be talking about today was done with a few groups, which I guess it goes back to when I was doing this slide yesterday, I was like, it goes back to basically the description of the history that Fernando mentioned just now. So this would be the Rome crowd is mostly theorists, and I'll present a few of the ideas that we've been developed since I was there with them. Then this is a weird crowd that it was, most of us were either grad students or postdocs at when I was in the US in the same institution, and since we've moved on to back to our countries, I guess most of us, but we are still collaborating. I think it's kind of cool. Like we sort of got independent from the supervisors and so on. We are working together quite a bit. Then there is Cabe, an experimentalist I work a lot with. I also met him around the time I was in the US. Same for this crowd here, a bunch of theorists. Rafael, who was my advisor and has since moved to Urbana. But we still have some collaborations going on with people in the university. And then I'll also present some results or a glimpse of what I've been doing with local people, with people at the DIPC. So Fernando, Miguel, who I also saw before there, and Maya. Again, I'll just give glimpses about all of this. So in order to do that, so the outline would be, I'll give a brief intro about quantum materials. I'll be talking about states of matter, electronic states, collective states, and I think even though a few of you probably work on superconductivity, maybe you're not so familiar with the history of it, and I think it's nice to hear it at least once in your life. I think it's the first time I tell this story. It's a cool story. So at least, even if you don't get many of what I say about my research, at least you learn something from this. I certainly learned a lot. And then I'll basically mention two things or phenomena that have to do with two things. The first one is ferroelectric metals. And if some people have heard about these words, so they usually don't go together. I'll explain a little bit why it's called like this. This may be a recent concept, new concept. And then something about TMDs, transition metal dichalcogenides, which is some material that, in Miguel's lab and several groups work with here at the DIPC. Good, so quantum materials. When I talk about quantum materials, I don't want you to think about Fermi statistics. So I think different people define it in different ways, or thinks about it in different ways. But I think my favorite is goes back to ideas of Phil Anderson. More is different. It's a very entertaining article if you haven't read it. And it has to do with the fact that collective behavior can be very different from the behavior of an individual electron. Okay. So going a little bit into more details, it would be you have the electronic wave function, and due to entanglement and or topology, you get a rich variety of quantum phases. So this goes beyond Fermi statistics. Once you get these things going on, these new phases, these quantum phases, have new types of particles. They're called quasi-particles. And these ones are very different from the original particles, so from your single electron. Okay. So some examples here, what this type of quantum phases can be. So this is uniform d order with an antiferromagnet of spins. This is some isospin d orbital order, so strong spin orbit coupling, charge order. I'll talk a little bit about this talk. If I get to the very end, I also mention some of these. Sometimes what you have is several of these quantum states intertwined in the same material at the same time. Okay, so these are supposed to be different order parameters where A and B can be two different phases. Then you have superconductivity. This would be S wave, this would be D wave, and I'll focus like a lot of the thread of what I'm going to be talking about has to do with this phenomena, with this ground state. So I'll say a few words about this. Like I'll tell you the story, but why is it that we're still working on this phenomena, this thing? So superconductivity, back to 1911, I guess most of you have, so I mean, maybe not, have seen this. Ons was in his lab. He was the first one who was able to liquefy the helium. He was liquefying all the gases that could be. I guess helium was the last one. And then he managed, he was the first lab in the world, and he was like, okay, I can get down to 2 kelvins. What can I do? So he tried to do a bunch of things that didn't work out, and eventually he was like, let me see what the resistivity of metals do when you go to cool down to very low temperatures. And as often happens in science, they were expecting something. What they were expecting is that the electrical resistivity would go down, and eventually the electrons would sort of freeze in the material. And so the resistivity would shoot to the room. And surprise, surprise, that's definitely not what happened. So this is mercury. As you cool down, all of a sudden, abruptly, you have a drop in resistivity, and the resistivity drops to 0. So this was very surprising, at the same time very exciting, because you have dissipationless charge transfer. So basically, if you imagine a wire like of a SATA system, this is a phase transition into something else. So the electron, the single electron, there's no way you can understand a single electron doing this. It's basically, you can make a ring of this, you have charge flowing, you drive a current through it. Without a battery, it will flow forever. That's very exotic. And you do it without a battery, as long as you keep it to, of course, below 4K, which was at the time maybe one lab or two could get to. So everyone got very excited. Many of the great theoretical physicists at the time tried to crack to explain why is it that several of these metals were having this behavior, this new phenomena. All of them failed. And this is an excellent article by Jörg Smayan a few years ago, where he showed how, they all had like extremely interesting and elegant theories that eventually failed, but it's told in I think in a very nice way, where it's just part of the scientific, let's say, yes, evolution or form of, how you go forward, right? Like it doesn't have to be a theory that eventually can explain it all, but a lot of insights got out of all these failed attempts. Few years later, the second and maybe more important property in this system, in these superconductors, was found, which is that simultaneously that you get dissipationless charge transport, the system expels a magnetic field. And this was discovered by these two scientists, and is typically called the Meissner effect. Okay, and this got also again scientists very excited. Like, why is it that this is going on? There is no way you can understand this type of behavior or phenomena by thinking of one electron. Okay. There's just no way. And actually, many of them tried again. Another bunch of so it was the first wave for dissipationless Q charge transport, and then Meissner effect, and then a lot of Bardeen, Heisenberg, London, Born, Froelich, Feynman tried, failed. So it was almost half a decade since the discovery that Bardeen, Cooper, and Schrieffer came up with the explanation and came up with a microscopic theory. So these, they were showing how, starting from the basic interactions between electrons and ions, the electrons, so you have an interaction, the electrons bind, form a bound state into what's called a Cooper pair, okay? And then they condense. So this is a boson now, and then they condense, they form this condensate, and now starting from the properties of this quantum state, so this is a coherent quantum state, they could so basically explain all the experiments that were out there. I'm not sure there is any other theory who has been able to explain so many other experiments. Like, it was extremely successful. They got the Nobel Prize for it. So I have to say at this point, why is it that people were so excited and they wanted to understand what was going on? So already around this time, when Owens got to think about electromagnets. Because if you have like many applications use magnets, and if you have, this was on where I did my PhD, so Ørsted showed how if you have a current in a coil, you create a magnetic field. And then he thought, hey, I get a coil, I get the current flowing, no battery, as long as I keep it cool, I get very large currents, therefore very strong fields, much stronger than any other permanent field. And I doubt he was thinking about these things like MRI, containing plasma infusion, particle accelerators, superconducting qubits in quantum computing and so on. But this is the type of applications or technological applications that these quantum phenomena are used in. Now, unfortunately, when he was envisioning this type of superconducting magnets, I guess they called, which nowadays I think the record is they got to something crazy like 50 Tesla, something like that, which is probably just in labs, like this huge. For these ones, I guess it's 20 Tesla. So the problem is that they couldn't do it. It took like many decades until these things were going on, and for that you had to understand why. Why is it that you basically couldn't sustain these currents before the system was like, I no longer want to be a superconductor. So it took a while, but slowly this is critical temperature. This is time, years. So since the discovery of mercury, then there were a few of these elemental metals. It was very slow, I guess. I mean, probably there were very few labs who could get to these low temperatures at the time. They also didn't really have a guide as to like, okay, how do you find a new superconductor? So there was at the time a very famous, or a guy who got famous because he discovered he's the guy who discovered most superconductors, I guess, ever. And he had this he had these rules which were empirical. It's like high symmetry is good, high density is also good of electrons. Stay away from oxygen, stay away from magnetism, stay away from insulators, and stay away from theorists. So nowadays, looking at all the new materials that were found, I mean, he was extremely successful around the 50s and the 60s finding all these materials, but we know that many of these, and this is not a complex, it's not a complete figure, but many of these not only do not fulfill one of these, like basically almost the opposite seems to be true, at least for the first 5. I don't know about the 6th. So I was thinking about the 6th, and then I came up with this, but maybe this is an exception to the rule. So Ashcroft was, I guess, a theorist trying to, look for high TC in these systems, and well, voila, you have hydrates nowadays. And I was also surprised to see this. I didn't know that he had an affiliation here at DIPC. Okay, so was anyone else surprised? Well, this
I didn't know either.
you didn't know? Okay, I was like, wait, DIPC, like, okay.
But this is very famous, so it's normal, right?
Of course. Why was I surprised? Okay, so I said like that there was a, the BCS theory, and you have like how to explain all these phenomena. You just have to form a Cooper pair, and this is like not obvious at all, and no one really at the time was thinking about bound pairs, not Landau, not any of these people working on phenomenological theories, and it's very anti-intuitive because, if you have an electron and you put it close to another electron, they repel each other. This is Coulomb. And so there is a nice paper by Ginsberg saying that one of Landau's favorite theses was nobody has yet repelled Coulomb's law. So how do you do it? Why is it that you get electrons pairing in pairs? So there is several ways of doing it. In the original idea by BCS, this is a retarded interaction. And I guess, again, this also gives you some insight about why it took so many years for them to get through this to this explanation, because you need the many-body formalism or theoretical tools to explain this. So basically, an electron, this heuristic picture, an electron comes in, interacts with the lattice, it polarizes it. Maybe some of you have already seen this. Then it leaves, and then after a while, the second electron will fill that polarization cloud that the first one has left, and then is attracted toward. Okay, so instantaneous repulsion that you cannot beat, but then after a while, attraction. So repulsion and then attraction, and that's how you can do it with phonons. And typically, this gives you a Cooper pair wave function, which is uniform. It's called S-wave. So basically, you have it on the same side. So an electron comes, leaves, and then the second electron will go to the same area, and that's how you get the pair. Unfortunately, many of these, or unfortunately, or like that's life, many of these systems could not give you a reason or a sufficiently large attraction from phonons to superconduct. So other things had to be proposed. And around this time, several groups at the same time, there was this proposal that maybe magnetic interactions, magnetic fluctuations, they exchange. So now the electrons are interacting through a magnetic fluctuation. So an electron comes in, polarizes, let's say, some electrons, and the second electron feels that polarization, now spin. Now it's an exchange interaction, and you form a bound. The quirk or the nice different thing, the peculiar thing about this mechanism is that it is now instantaneous repulsion. This is Coulomb, so there is no retardation. There's no time that the second spins like, oh, I'll wait for a little bit, and then the other one goes. I mean, this is Coulomb-Coulomb interaction. This is pairing from Coulomb. So how is it that they beat what is it that they do similar to this? Well, they make nodes in the wave function. So now you can think that the solution that of your ground state is such that these two electrons in the Cooper pair are always like farther apart that they would be in the normal state, and that's how the system lowers the energy. So in the case of, for example, D wave, they are never on the same side. You can think about this Cooper pair living in nearest neighbor sets. So, okay, so that's how you get a pairing. Explain in a few seconds. Okay, so I gave a couple of examples of how you get the superconductivity, how people nowadays still, I'm not sure there is a systematic way of searching for a particular material, but typically what happens in these systems, in these quantum materials, is that you get very complex phase diagrams around superconductivity, and that gets us entertained for many years, sometimes, I guess. So there is I mentioned phonons, which is the lattice. I mentioned magnetic fluctuations, so heavy fermions. These were in the 70s, cuprates in the 80s, iron-based superconductors in 2008, TBG. So every about 10, 12 years, there is a new family of materials found, and today I'm going to discuss two other examples, because there is more than this. So this is a new example that I've been thinking about for the last few years, which is now, instead of exchanging phonons or magnetic fluctuations, you exchange ferroelectric fluctuations. So the idea is pretty much the same. You get an ordered state that is, ferroelectric. You have some fluctuations nearby that the electrons will use to form these Cooper pairs. And the second example is this titanium diselenide, where there was this proposal that you can get maybe superconductivity from fluctuations of an incommensurate charge density wave. So now the ordered state here would be ferroelectric, and here the charge density wave, and then you can get pairing. So I'll give you a few flavors or a few some taste about these two. So let me start. Is there any questions so far, or now I'll get into some more technical details. So the first one, as I said, this is a sketch. So say that you have an ordered state, which is a ferroelectric, which I'll explain a little bit what it is. And then you have a dome. So this ferroelectric is essentially a way for the system to store electrical, I guess you think of having electrical dipoles. So as you lower the temperature, you have some ferroelectric phase, and then the system goes through a transition into a new state. It's one of these new states where you get a finite dipole, okay? So up here, you get a soft mode, which is a transverse optical mode. So this is something that is polar. It's a dipole that is fluctuating, and then it freezes. And this mode was measured, I guess in this case, was neutron. So as you lower the temperature, this mode gets softer and softer and softer. Eventually it goes through zero and goes through this phase. And now the idea is, how could superconductivity or the electrons use this to pair? And why is it that we are even thinking about that? So there has been a lot of experiments showing how, if you move this axis, so just for the sake of clarity, I have separated them well, but if you move this axis, so you basically start doping. This is the charge of the electrons. It's happening electrons here and here and here. The closer you are, or the proximity of to this phase really affects DC a lot. You get an increased in TCs of like a factor of 2, 3, and so on. And so the experiments are suggesting that this phase is affecting it. And then what could be the initial ideas? What could be the pairing mechanism? What is the resulting condensate that comes out of this. The challenge is that these are very typically very low, dense systems with very low, very few electrons. And this is certainly outside the BCS paradigm. So there is a few things in order to use the formalism. There is a few things that are a few checks if you want, and this one like doesn't check many of them. And then the next, the next obvious challenge at the time is how do you couple the electrons to this ferroelectric mode? So typically these two communities are very they don't talk to each other. I guess they haven't had much overlap over the decades. So I guess people from this community are not used to think about ferroelectrics, and people in this community are not used to thinking about metals, I guess. Okay, so this is for some reason like there is a hole, like how do electrons couple to this? So this is the only equation of this talk. So the coupling to polar modes. Let me show you what, like, I think maybe some people in the audience, if they're used to thinking about phonons, they think, well, this is just the coupling to the phonon. What is special about this? And the special thing is this is a polar mode. So if you write down the possible coupling from symmetry, so you have an electron here and the second electron here, and they exchange this mode. And then you can, so this is a spinor. So you can have the typical, this is the usual electron phonon coupling, Q.U with sigma 0. So it's the same for both, say, pseudo spin up, pseudo spin down. But I said that this is a transverse optical mode. So if it's transverse, it means that these two things are perpendicular, therefore it's not allowed. Then you can say, okay, let me go to the next order, that periodic quadratic. This is very like exotic. It turns out that in these systems, this can be relevant, but it's not what I'm going to discuss today. I think it's much more interesting to stay in linear order in U, so the still linear order to this polar mode. But then by symmetry, you can also have this thing, which is K of the electrons, so the momentum of the electrons, and sigma of the electrons. So this is something that is a dipole, that is non-magnetic. It's just an electric dipole coupling to the spin, and this is very strange. It's RASBA-like in the sense that you can think that you have these electrons where the spins are degenerate, and when you activate this polar mode, it sort of creates this RASBA-like split, but this is dynamic. Okay, so the first thing that we did was, okay, this is allowed by symmetry. How do you get it in these systems? And we showed that you can, it's not so necessary to, so the spin orbit coupling enters to some extent, but it's not directly proportional to the coupling. And so you can have something called orbital RASBA or spin RASBA. And this, as often happens, led to, like, we realized that some tools in the toolbox were missing. There were some extra implementation that needed to be done, and so on. So there is, the take-home message from this is the coupling to these modes is highly non-trivial. Okay, and it's linear in K. Now that has consequences, and going back to pairing, it's like, okay, now I know how it pairs. Let's say that it goes with this weird form. What is the first thing that one says is that you are coupling to essentially a mode that is like a phonon. And when you solve the pairing problem, you typically get a hierarchy of where would you get attraction, right? I was talking in the beginning, like how do you get attraction out of, like, so that the coupled pairs are bound. And you get attraction in the S, I mentioned it before, the S wave, the one that is uniform, the one that typically you get from phonons, but you also get attraction in P wave and D wave. And this is extremely non-trivial or maybe unexpected, because from phonons, you never, all these channels are always attractive. You never get attraction. Good, so this is, let's say, the first message, or the first result, that if you couple to these modes, you can first of all get attraction, and then you get several channels that are competing. The second one is you get a dome. It comes naturally out of this. And without going into details, so now then it was like, okay, let's take a material and really work out the entire theory and see how much of it agrees. And so the dots are the experiment, and the line is this theoretical model. We assume that the electrons are coupled to these ferroelectric modes. You have to go through some like technical details of you have to go through the strong coupling pairing analysis. So there is a quantum critical point. In order to do that, you can no longer do BCS, and you have to do some dynamics with the Elias group and so on. But other than that, it works pretty well. There was some criticality that was unexpected, as in you get a peak of TC inside the ordered phase, which is highly like not. I don't think it's very conventional in all of at least in all these other. Or it hasn't been pointed out, the other mechanisms were with magnetism and so on. Good, these two things. The next thing I wanted to mention is while we were thinking about these things, like people in the labs, they kept designing new things, and as usual, reducing dimensionality is one of the things that people do in the labs. So in this case, they did heterostructures, so they sandwiched one of these oxides which are close to this ferroelectric instability, they sandwich it with different things. And there is a two-dimensional electron gas. So you can imagine that up here there is something else, and something else can be very different. The end result is the same. You get a two-dimensional electron gas. And surprisingly, so this got a lot of people like making these materials. Surprisingly, TC went up a factor of 10. And like, we still don't really know why, to be honest. The main difference, like, depending on what material you put, if the spin orbit coupling goes up a lot, and maybe, so the spin orbit coupling definitely goes up a lot. So maybe having 5D electrons versus 3D electrons is could explain this. I don't know. The other big puzzle is that depending on how they grow these systems with the crystallographic axis in different directions, TC go from like 2 Kelvin, 1 Kelvin to 0. Like this is also like not very typical. And this could give hint into like what is the pairing mechanism, why is the system doing this? And once you understand that, basically also like how is it that I got a factor of 10? So that's what would be nice to understand. And so now I'm going on Monday to EHU, to PV, to talk to this group, because they have developed a very nice ab initio implementation to see molds in slab geometry. Okay, so maybe they can tell me something about what happens to the ferroelectric mode when you confine it to 2D, and how it couples to the electrons, and whether one can then explain these two things. Something also very interesting that happens in this system is that there is a strong violation of Pauli limit, and what that means and why that is typically interesting is superconductivity does not like magnetic fields, so it expels it. As I said, that's the Meissner effect, but it cannot expel it forever. Like at some point, it's like, look, energetically this is not favorable. I'm no longer happy. I'm going to go to normal state. That's why in the beginning also they couldn't do electromagnets with very high fields. So you can think about, there is these supercurrents that are connected to some critical field, but I think even the more conservative way of looking at it is you have the Cooper pairs with the spin opposite, and now you're putting a magnetic field, and one of them is going to say, okay, I'm going to start to, orient with the magnetic field because I'm getting energy or Siemens, and at some point, if that energy is much larger, the pair saying, I no longer want to pair, and you break the pairs, and then you go back to normal state. And these systems break this Pauli limit by a factor of 10. So you expect to destroy superconductivity around, I don't know, I think it's like 2 Teslas, and they survive up to 20, or 3 Teslas up to 30, something like that. And this is interesting for two reasons. The first one is it probably gives you a hint of what kind of pairs are you creating so that they are so resilient to magnetic field. And the second thing is very interesting from the, I guess, more application kind of way of like, you have something that can sustain very, very large fields, and that's interesting. So in these two papers, we propose two mechanisms for being so resilient. And I don't know which one is more important. In one of them, you have new quasi-particles that have reduced moment, so then basically they can uncouple to the field, and then you can sustain superconductivity for much larger magnetic fields. And the other one is you have strong spin-orbit scattering. You can also minimize the paramagnetic, this effect of coupling to the field. Good. What else is interesting about these systems? Yes, the flexoelectric coupling, something else that I've been working on. So like I just talked about this polar mode, but there is very recent reports that there is some extra mode very nearby that is basically the transverse acoustic mode getting soft and crossing or freezing at a finite momentum. So this is the if you have a new lattice instability, a new state, and so we were all so focused on how the electrons couple to this. Well, it turns out that maybe this is not actually the right way of thinking of these bosonic excitations, and you need to think about some like these two things coupled, and that's in these systems that's basically having a significant flexoelectric coupling. And so what we've been doing the last year or so is together with these people trying to first of all quantify and see from ab initio whether this is true, whether you have this flexoelectric coupling, and indeed it is. So in principle you can get numbers and they are substantial. And the second is how would these electrons now couple to this mode? And the answer is like they do change it a bit, and they do, like taking into account this part, gives you a substantial contribution. So you basically coupling to the quadrupolar charge the electrons. And now the next step is like, what does this mean for pair? And that we don't know yet. But it looks like it should help, definitely. Another thing, this is another collaboration with an experimental group of Damian Pelch in Croatia. So I've been thinking a lot about NMR as well. I don't know if there is people doing NMR here, but this is basically it's a really great tool to characterize charge carriers. And basically it measures the spin susceptibility. So whenever you need to understand what's going on in a system, it's good to be able to characterize with using different probes the electrons that will eventually go into any quantum phase. So in this case, we got to characterize very carefully, very extensively these charge carriers that basically challenge the status quo up to now in these systems that were reporting very unusual metallic state. It doesn't seem to be much very unusual, at least from the spin susceptibility point of view. And with this, I'm getting to the end of the talk. I'm gonna briefly quickly switch gears towards TMD. This is yet a different set of materials that I've been thinking about with Miguel's and Fernando's group here. Again, connection to superconductivity. So in this case, you have a charge density wave and superconductivity. This is titanium diselenide. And in this case, you also have a charge density wave and superconductivity. So I'm only gonna say a few things about this. So the idea behind this is these beautiful measurements in Miguel's lab with an STM tip on a monolayer of this system. And as you lower the temperature, what you see is that you get these modulated stripes. So the electrons are organizing themselves in this way, and the question is why? Because in principle, looking back at this, the superconducting state would come out of that weird state. So first one needs to understand that weird state. And then, so the most important thing I think that came out of this, I don't know if you saw last week, there was this, I think I actually saw it in El Correo or in the media. So they've measured the world's smallest Lauburu, right? This is some molecule, nano, graphene, something. So I think Miguel has measured the world's smallest Irulerico Escua. I don't know if there is many Basque or like people who have been around for a while, but this is an archaeological, semi-recent archaeological found. It's supposed to have these Basque words from this, 1st century before BC, basically. And, I think they've measured this charge density with this electronic reorganization could be the world's smallest Irulerico Escua. Okay, so what's going on in this system? Why are the electrons doing this sort of phenomena? And this is just the last slide. So the idea is the following. You have this is the phase diagram. You have a charge density wave, which is basically spontaneously the system decides, like, even though when you look at the atomic, from the atomic perspective, it's the same atom, the same atom, the same atom, the same atom. For some reason, and we're going to be agnostic as to why, it's a whole different, it's very interesting to understand why. All of a sudden, you see that when you come with a microscope, they start to say A, B, like up, down, spontaneously, okay? And in this particular case, the way of doing developing this new order, which is basically, charge modulations, has 8 possibilities. They are all the same. And typically what happens in the system is that you lower the temperature and the system chooses one of them, and that's it. And this is what has been measured until now. You lower the temperature, you have this long-range order of one of the states. The system picks. There is something very cute that happens when there is an incommensurate charge or instability nearby, and that means that instead of, so this charge modulation typically is a modulus of the interlattice spacing, but sometimes it can happen that the system prefers to do it with any rational number. So it's not every 2 or every 3, it's every 2.2 or every, and the cool thing about this is that the transition from going from a natural number to this other possibility has to go through what's called a nearly commensurate state. And in such a state, the system basically flows through different ground states in this fashion. So what you're looking at here is basically domains of the system going through the different ground states. It's like A, B, C, D, A, B, C, D, A, B, C, D. So how do we, these claims are based on, we've done the symmetry analysis and using some phase locking techniques, we have extracted all the information of the other parameters. And importantly, so first of all, this happens in very unidirectional things. So if you remember the phase diagram that I saw, like people thought that superconductivity would come out of this 2-dimensional array of electrons. This is certainly not true. This is like unidirectional. There is definitely like 3 types of direction happening. This is not a 2-dimensional array. And the second one is that the mechanism was proposed for Cooper pairing in that case was some phase fluctuations of this charge density wave, incommensurate charge density wave. And it turns out that when you extract all the information, these are two intertwined real CDW. So there is no phase degree of freedom. So now, I'm not sure how or if whether this type of state would actually give rise to a pair. And then what we also find is that there is two other parameters. One of them is the driver, the primary, the other one is the secondary. And the secondary seems to be crucial. So if it is crucial, also like what is its role for pairing is not clear. And this is it. I think I've talked way too much. This was like a glance of the things that I've been working on. I'm not even sure for how long I've been talking.
Almost 50 minutes. There's still time for questions.
Okay, so I'll stop here and I'll take questions. Thank you for your attention.
Yes, so thanks for the talk. And are there any questions from the audience? Ivo?
In the part about the ferroelectric mechanism for superconductivity, so was it important to be ferroelectric in the sense that the polar state is switchable, or could it just be pyroelectric, so just to have a...
Pyroelectric works perfectly fine, actually. Yes.
Because you emphasized at some point the word dynamical, but I didn't understand exactly what you meant there.
Yes, so dynamical in the sense that when, as you say, so when the system is pyroelectric, this is a mode that is, let's say, at low energies, but it's not frozen. So you can imagine that this is a fluctuating dipole, and this fluctuating dipole will couple to the electrons. So in that sense, you can imagine that in a dynamical way, these bands go like, and you can get pairing out of that, basically. Also in the ordered state. That's probably even more interesting, but you can get it in. So the phase diagram that I thought we work through the critical point into the ordered state. And there it's even larger because you have extra coupling, but in both. So you get it at both sides of the ordered and ferroelectric and pyroelectric. And the systems are in the real material, let's say, happens in both as well. So of course, the closer you are to the state, the larger your coupling.
I think there was another question back there, and then Emilio.
Thanks for the nice talk. I have just maybe naive questions. So first is that can you describe how the Meissner effect takes place in 2D materials? I cannot
In
imagine.
2D?
Yeah, in 2D.
Yeah, me neither. I guess it doesn't. But so yes.
So 2D materials, superconductors, they cannot repel magnetic fields.
They cannot repel. You certainly you certainly get a critical field. So I don't know if it's repelling, because it's you're thinking of just like one. I mean, I'm not sure how to like. So the. I mean, you get you get critical currents, but the field will just, go around it and eventually through it. So I don't think, I'm not sure you can measure the Meissner effect in a 2D system. Yeah. So I always think about it in the bulk sense as Meissner, right? Yeah. Another thing is how the field will interact with the condensate in 2D.
I just cannot imagine. So, and my second question is that because you were presenting ferroelectricity, but for polar materials, right? So
yes, it's a synonym for me. So when you have ferroelectricity, you develop a polar axis.
I mean, because let's say I'm aware that, for example, in layers materials, then you can have ferroelectricity. In maybe like the theory is due to the sliding of the layers.
Maybe.
One of the theories is due to the sliding between the layers.
Sliding.
Yeah.
Okay.
Like even, for example, like I see that in nanowulle they measure graphene, even monolayer graphene, they have ferroelectricity, for example.
Yeah.
And so, but then this theory is applicable in those cases or not?
So if you have a mode associated to that particular physical system, which I'm not sure. So I don't know whether it's a mode that gets soft and that the electrons can couple to. But if that's the case, then yes. Now I know that not all ferroelectrics have this soft mode. So yeah, I was maybe I should say the ones that I was talking about is the ones for which sometimes they call incipient ferroelectrics. So that's for sure what I can say that works. Then in general, the mechanism for which a particular system goes ferroelectric can be different. And then you should look at what is the fluctuations, because it could be very different type of fluctuations, or the mode, or maybe there is not even a mode. Maybe it's this improper ferroelectric zone. And yeah. But if you have a mode, then it should work. Another thing is whether the coupling is large enough. So the coupling is going to be there. If it's 10 to the minus 10, you cannot do anything with it.
Maybe just one final question, because the last slide you showed like a charge density wave, right?
Yeah.
And I saw that is inverse Fourier transform from the endpoint. So it means that you first take the Fourier transform and then you choose some signal and then you Fourier transform back to real space, right?
You mean this thing here?
Yeah.
Yes. 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 So there is some peaks associated with the charge density wave. You take, because when you do Fourier transform, you get all the harmonics contribution from the lattice. So you'll have the ones from the just Bragg peaks, let's say. Then you'll have new order, and then you can select those and then Fourier transform back. And that is the ones that have to do that wave vector, which is, in this case, is half of the Bragg peaks. And then you get the, go back to real space of where that charge density wave order parameter lives.
You focus on the endpoint because the end peak, because this is where the superconductor comes from.
No, I focus on that one because that's where. So if you are at high temperature, you get only Bragg peaks, that G, and if you look at the endpoints, there is nothing. And when you go through the transition into the ordered state with the charge density wave, they will give contribution to those points and harmonics. So M plus G, M plus 2G, and so on. And if you want to know about that part of the electronic mambo jumbo and filter it through all the rest, you look at those peaks. So those are the ones that have to do with the new order, which are in the high symmetry phase, they are absent.
Emilio.
Yeah, thanks. That was very nice overview. Have a question going back to strontium titanate.
Yeah.
Which is a very strange beast.
Yes.
It is. It was called quantum ferroelectric before
Yes.
the quantum became a furore.
Yes.
But and it is because, if I understand correctly, that is because even at 0 temperature, the ground state, the nuclear ground state, is above the minima, if you want to see it like that. The 0 point motion covers the several minimum. I couldn't see through your coupling terms whether that is precisely what you're capturing or is something else.
I would say yes. So what I'm capturing is the basic, the minimal, let's say, coupling to this mode that eventually freezes. So
But freezes to one particular minimum of the energy, or freezes to.
Yes.
That's the question. What does it freeze to?
Yes, to one of the possible Q equals 0 states. Yes. So I mean, you probably what you have in mind is this double well, right?
Yeah, it would be 6 wells.
6 wells, it's cubic, or yeah. So yes. So when this mode, this propagator freezes, it can go into one of those. Yes. But why wouldn't it? This may be.
It does it when you dope it. When you dope it, it does become a ferroelectric.
When
And
you
then
do,
it
I mean, when you
freezes-
can do, yeah, you can do many, yeah.
Sorry, when you isotope dope it.
For example, yes, you can
then it's to
also,
one of the minima.
yeah,
Then
That's
yeah,
right.
then the ground state, the 0 point motion is above one of the minima. You can see, you can make a phonon expansion about it easily.
Yeah.
But the isotopically normal
yeah,
is intrinsically an harmonic.
yes. It is intrinsically an harmonic, but then I'm gonna do the experimental viewpoint here. So what is this then? What are neutrons measuring?
Sorry?
So this is the neutron measurement of this mode. So it is intrinsically, I mean, there has to be an harmonic effect, but they can follow this particular mode. And I can always say that this in the harmonic approximation includes all the, I mean, I have a well-defined excitation, right? That I can follow, that will include all the complicated and harmonic effects. And that's gonna be my, if you want, renormalized propagator for a phonon. Because in reality, the reason that I have this, even, I guess you can probably already you can probably see it here. I mean, there is certainly a strong interaction between this mode, just let me take one of the modes, and this one. So for sure there is an harmonic effect, but I can still experimentally see a mode, this TO mode with Raman, neutron, and so on. It's a well-defined beast.
What I'm somehow seeing is that there should be a mode, but it would be a non-polar mode, actually. The polarity develops with a broken symmetry.
Oh, no. So, okay, that I can answer. The rep is T1U. That's polar. You work out the
So that's
T1U. It's polar. Q equals 0, 1. It's optical mode. So it you do infrared. It's infrared active mode.
yeah. No, yes. What I mean is what would be as a reference you would have as a non-polar solid. The polar mode, you can have a polar mode around the minimum, which is symmetric.
Yeah.
Yeah, you have 6 minima, and your wave function is symmetrically above them. That's what I'm saying. But anyway, I think that's getting a little bit we can discuss it.
Yeah. I mean, I think I know what you mean, but I still think this approach is justified in that sense. But
yeah, maybe I'm remembering incorrectly. But isn't there a strontium titanate? It's like at 0 Kelvin. It's antiferroelectric or antiferroelectric, so it has like a zone boundary mode.
Yeah.
That goes off. And does that have any influence on the superconductivity?
That happens at 110K. So
Also, you're looking at this antiferroelectric.
you are deep in that phase, actually. Yes, it's tetragonal.
Okay.
Yeah.
So okay.
So these anharmonic effects that we were talking probably are also important at those high temperatures. But by the time you get from 100 to 0.2,
And the reason why you need a soft mode is just so you have a large atomic displacement, so you have a stronger coupling.
no, it's so that the theory is controlled. So you can always do BCS with something that is much faster than the Fermi energy, but I mean, I'm not sure what it means, the result. That's one of the challenges in these systems when you have very low Fermi energies. You need modes that are least comparable to the Fermi energy. If they're going to be much faster, who is renormalizing who?
Any more questions? No, we can thank Maria again.